All right, so welcome everyone. I'm An Chen. I would like, before we get into the InSAR series, so I would like to first give a brief introduction of the course about our agenda. And then Melissa and Becca will help us with introduction of the Sage Gauge and EarthScope, and we will take a class photo then. So let me get started. So this course, we are fortunate to have a group of instructors who has years of experience in InSAR processing. I would like to thank for their time to contribute to the short courses run for years. I joined fairly late, but I'm very happy to be part of the team. The course was organized in the following way. So we will have a plenary session that go over the InSAR series and some of the processing strategies and the noise and applications. And that's the first Monday to Wednesday this week. And all of our instructors will host some of the sessions in this plenary session. And for those of you who later assigned for the optional breakout session, then your instructor will reach out to you regarding to the time for those breakout sessions. And through those breakout sessions, we can work through some of a set of the homework so that you could learn how to use GMTSAR to processing stacks of interferograms and then do some surface deformation analysis. So here is a brief objective. So the very first one, understanding principle of SAR and InSAR. So this is covered by the plenary session. And also in the breakout session, we are going to try to help you to be able to run GMT, get GMT and GMTSAR installed on your own computer and be able to process generated interferogram on your computer. And so as based on your level, because of the class, a student typically coming to the class with a different level of background. If you're new to InSAR, I think it's a good goal towards the end to be able to generate a set of interferogram. And if you have a prior experience and it's a goal to maybe refine some understanding of the noise mitigation strategies and probably perform a robust time series analysis. And here is our agenda. So in Melissa's announcement, we blocked a 4-hour session because this class used to be a 2-day class for the plenary session. And follow Eric's suggestion that it's Zoom fatigue, so we decided this year to spread it out to 3-day plenary session. And so that's why we anticipate the first day of session lasts maybe slightly less than 3 hours. The second day is the same, and the third day should be a little over 2 hours. So it will be shorter than the 4-hour block. So hopefully people can go grab their lunch after the course. And so at least if I'm in Austin, that would be kind of around that time. And so in day one, we are going to mostly go over some of the theory behind how the SAR algorithm works to form high resolution image, the orbital information, and how you could use SAR image to form interferogram, and also talk towards the end of today, the SAR imaging geometry about that is really with the recent SAR missions. And on day 2, we are gonna talk about the actual data access. And Matt Lay will talk about two-pass tool that give you a demonstration of how you can use GMTSAR to generate interferogram. And also we talk about Molly Zepker and Roger will talk about the noise and phase filtering about mitigate the decorrelation noise and atmospheric artifacts. And towards the end, the section 13 and 14 is actually a combined session that Katia and Catherine will talk about the batch processing and also InSAR time series analysis. And on day 3, we are gonna cover a few examples of applications once you know how to process data in different science disciplinaries, as well as Ding Liu is going to talk about some of the latest development of GMTSAR, trying to use Python as the scripting language instead of the C#. And at the very end, Katia will give a brief update about the NISAR mission, because we are all waiting for a long time and excited about it. So hopefully we will have this kind of data in near future. So that's the agenda. So roughly 2 to 3 hours per day. And I'm very excited about this session. Every year when I take the session. Actually, it's also a very good review for myself about the theory behind the thing. So, and after this, I want to give also a very brief review of the GMTSAR short course. So it was developed long before I joined the GMTSAR and the script. So initially, GMTSAR was a software package that was developed at a script and used for their research group. And they started the GMTSAR classes in person at script starting from 2011. I believe this is a photo from the first GMTSAR classes. And over a year, the materials was developed through the contribution of instructors, a grad student. And so, this I think is at the first time it was done at UNAVCO in Colorado, Boulder. And it just has been going on. You can see the size of the team start to grow and expand over time, and also expand. This is Xiaohua Xu, first time giving these classes in Chinese academic of science outside the US. And there is a major change is around 2020 when this class switched from the in-person class into the virtual class. I have to say it goes both ways. People appreciate that in-person experience, but the idea of being able to shift the class from virtual to from in-person to virtual means we can start to accommodate a larger team of participants. And so in some way, I think that's a good move, because ever since then, the class size grown from tens of students to hundreds of students and be able to reach to more people. And the lectures are recorded and openly available on internet. So for this class, you will be able to have a Moodle account. This is the first year we use Moodle. So all the lecture materials, and I believe later the recordings will be available on Moodle after each day. And then also it will be available online. I believe there is a Google Drive document, but we can announce those. So after the class concluded, you will be able to find these lecture recordings on EarthScope website as well as YouTube. And as you can see, there is a picture. So after my introduction today, we're gonna take a picture like this, because after maybe 15 years, when you look back, and that's just and you kind of recall how this class evolved. And I think that's very good. And before I move to the EarthScope introduction, who hosted all these classes and supported these classes over years, I also want to mention the course lecture materials was developed over a stretch of, I think, 15 years. And also later this summer, there will be a companion textbook that will be available online. You don't have to buy the actual physical book, because it is openly available online. And that actually covers all the lecture series that we're going to cover here. So that is going to be a useful reference later on if you want to learn a little bit more into the series. So later this summer, we will have a book available that is matching the GMTSAR software. And we will make that announcement and provide the link of the textbook once it's available online through the Discord channel and also through the EarthScope email list. And before I hand it to Becca, so I would like to mention about the course. So we have expected behavior. We should treat others with respect and consideration, value diversity of views and opinions, be considerate, inclusive, respectful, and collaborative, be kind to others, avoid personal attacks, communicate openly with respect for others, critiques idea rather than individuals, be mindful of your surroundings and your fellow participants, respect rules and policies. We are not meeting in person, but also respect rules when we communicate virtually. And all communication should be appropriate as a professional audience, including people with many background. And so that's I just want to briefly review that. There are some other unexpected behavior and consequences and reporting strategies. So I will hand it to Becca for some additional introduction and welcome.
Thank you so much, Anne. And I really just want to thank all of you all for participating in this course. I mean, a special thanks to the instructors who give so generously of their time and expertise. They're volunteers, so that's absolutely amazing. This is no small feat. And also thank you to all the participants for getting involved and making the choice to learn a new skill or improve a skill you're already working on. So in case you don't already know, this course is sponsored by the EarthScope Consortium through the GAGE facility. So that's some words that you might not exactly know what they mean. So the EarthScope Consortium is a nonprofit organization, and our mission is to support geophysics in all of its forms, but particularly seismology and geodesy through operating two National Science Foundation large facilities, one called GAGE that supports geodetic infrastructure and capacity building, and one called SAGE, which supports seismic infrastructure and capacity building. And we're incredibly proud to be able to operate those facilities, and we're incredibly grateful for the ongoing support of the National Science Foundation, NASA, and the USGS that provide substantial support for those facilities. So one of the core mission or core values of EarthScope and those facilities is really to build and enrich and foster a community of scientists who are interested in Earth systems and the incredible planet that we live on. And so what does that mean? Like, supporting a community means things like this short course and actually the big portfolio of short courses that we offer, with the idea to like make sure that geoscientists always have really equitable, really open access to the skills they need to make new scientific discoveries. But we're not only interested in like structured skill building, although that is incredibly important. Please keep in mind that another part of this course is actually to build a community in the sense of the human interconnections that means. So, keep track of who says things in class that you think are interesting or inspiring, and the research of your instructors or your colleagues in the class, because lively and vital scientific communities that produce new discoveries both have skills and have those interhuman collaborative connections that help us all grow in our scientific endeavors and in our thinking and in our intellectual and social progression. So we're really committed to this short course, but then a whole portfolio of short courses at many different levels that are intended to let you all build your skills and build connections one to another. So that's really important to us. And I think we're very excited about the future, where those commitments to community building and capacity building will continue into the years to come. So you're now part of the EarthScope family and part of the SAGE Engage facilities. So you have both a responsibility and an opportunity to help one another become great Earth scientists and help us all as a species take good care of the planet we live on by understanding it as well as possible. So welcome to EarthScope, welcome to the GAGE facility, and welcome to this short course. And feel free to reach out to me at any time. Let me know how the course went and what we could do different, what we could do better, what we've done great. And we're really, as I said, committed to providing both the soft support for a very lively scientific community and the concrete support for infrastructure and software and education that this course represents. So thank you all so much, and I hope to see you in person at various meetings, but also, more important, read about and learn about the discoveries you make using the tools you learn here.
Thank you, Becca. And I think before I'm going to stop sharing so that Melissa might be able to help with course photo before we move to the lectures.
Yeah, there we go. Yeah, if I could get everybody to turn on their videos, their cameras. I'll give it a minute or two.
It's really great to see people from all over the United States and all over the world. Thanks everybody for getting up at whatever weird time it is for you and being involved.
Okay. Make sure we've got this. All right. I got a couple of screens that I gotta open up, so I was gonna take a few screenshots. So if everybody just looks at the camera, smiles, and I'll go 1, 2, 3. Okay. Let me get, oh, somebody just joined in. Let me get that. All right. 1, 2, 3. The second screen. People. And we'll go 1, 2, 3. Okay. Y'all can turn off your cameras now.
Thank you. And our next speaker is David Sandwell, and he's going to talk a little bit more about homework and the course.
Morning, everyone. I hope you can hear me. My name's Dave Sandwell, and I'm a professor here at Scripps Institution of Oceanography and a longtime developer of GMTSAR. And it's wonderful to see all these younger people here because I hope this continues on into the future. We have an InSAR coming soon, which could be really exciting. And we're in a golden age of InSAR right now. So I want to talk a little bit about things that you'll see again during the short course. First, a really brief overview, one slide about satellite remote sensing, and then talk about SAR and InSAR, mostly the geometry and some of the limitations. And then finally, this homework that I hope you can all do, even if you're not assigned to an instructor, you can do this on your own. And I think there's a link to it somewhere, but it's a way to get started. So in this brief talk, I'll first provide an overview of satellite remote sensing. Where does InSAR fit into this large group of satellites that are orbiting the Earth? Talk a little bit about the amplitude, wrapped phase, and correlation. These are products from interferometry, and we'll hear much more about this later, but this is just to get started. Also a little bit about radar coordinates versus geographic coordinates. The data are collected in radar coordinates, but we really want to look at them in geographic coordinates. And so it's good to know this distinction and how to transfer between the two coordinate systems. And then a little bit about unwrapped phase, how that maps into line of sight deformation. Okay, so one slide on remote sensing, and if you've taken my remote sensing class, this is my favorite slide, and I'll try to explain it in a few words here. But what you're looking at is a plot of the transmission percent of through our atmosphere. You send electromagnetic waves from space down to the Earth, they bounce off and they go back, and you have to get those waves through the atmosphere and the ionosphere. And there's only a few windows, a few wavelengths where you can do this. We could, of course, in the visible, you can see outside of the Earth. And then there's windows in the thermal infrared part of the spectrum, about 10 micrometers. This is about 0.5 micrometers. But then way out here at the microwave part of the spectrum, the wavelengths of like 1 centimeter up to 50 centimeters, the atmosphere and ionosphere are very transparent to electromagnetic waves. And so this is where we'll be looking out here in the microwave. And you can do remote sensing in two ways. You can have passive sensors, things like cameras that look down on the Earth, thermal infrared or electro-optical cameras, or a microwave radiometer. Or you could have an active sensor, one that sends out electromagnetic radiation in pulses, like a laser, a radar altimeter, or a synthetic aperture radar. So we're going to be focusing on this little bit of the remote sensing world. A little bit about SAR, and you'll see this again many times, but we have a satellite orbiting the Earth. There's the direction of the orbit, and I'll talk more about the orbits later on. And it has a large planar antenna that sends out pulses of electromagnetic energy. These pulses hit the Earth. It sends it off to the side, so this pulse sweeps across a swath here, and then the pulse returns back to the satellite and is recorded and eventually ends up on your computer on your desk as a SAR data set. And we'll be talking about a number of things like near range and far range and the footprint of the echo. But the most important thing right now is that there are two coordinates in this radar space. One is called azimuth. It's along the satellite track. It's probably not the best term, but it's the term everyone uses. And then there's one here called range. That's across the satellite swath. So that's a natural coordinate system for radar imaging. Actually, I'm going to skip this, but we're going to be looking at repeat passes of radar imaging, and you can do two things with that. You could look for deformation on the surface of the Earth. That's what we'll be talking about, or you can measure the topography of the Earth. I think Eric Lindsay will talk all about this later. Again, about this radar coordinate system, we have range and azimuth. This is an interferogram in a geographic coordinate. So north is up here, the way you'd like to see it. And there are three products here. There's the amplitude of a single SAR image or backscatter. Sometimes it's called sigma naught. There's the phase. This is what we're going to measure when we have two images and we difference the phase. And then there's the correlation. That's how well the phases are correlated, going from 0 to 1. And that's a third product. The color cycles here, you get one cycle every 28 millimeters in this case, and that's half of the wavelength of the radar. So how this interferogram looks depends a lot on the wavelength of the radar. There's C-band that we'll mainly be using, but there's also L-band coming along. Here's an L-band example. So, and also this is, when we talk about orbits, this is a descending track here. It's going from northeast to southwest, but you can also have an ascending track. The satellite's going the other direction from southeast to northwest, and an L-band is a longer wavelength, so there's 118 millimeters per cycle of SAR phase. So those are the main things. We'll be looking at C-band and L-band and in radar coordinates and in geographic coordinates. Here's just that mapping. When we first process the data, it's all done in these radar coordinates. Here's azimuth and range. But later on, we want to look at it in geographic coordinates. So you're going to have to, in this case, we turn it upside down. So it's, when you look in the radar coordinates, it's hard to understand what's going on. It's better to look in the geographic coordinates, but this is the way where the data are processed. Now, InSAR will have maybe a different form of processing called geocoded SLCs, but right now it's all sort of done this way in radar coordinates. One last thing, so we're measuring phase between -pi and +pi, and we have a formula to map that, that phase into line of sight deformation, and that's just the wavelength divided by 4pi. There's a factor of 2 because the echo goes down and it bounces and comes back, so you get an extra factor of 2. And there's a minus sign here because people like to have the red here moving towards the satellite. This is a big earthquake interferogram. This is the line of sight displacement, and there's the unwrapped phase. They're basically the same thing, just a different mapping, different color scale. One more limitation about radar interferometry is we only have two components of deformation. We have ascending orbits and descending orbits, and you can measure this called the line of sight deformation. It's the line of sight between a point on the ground and the satellite. And so that's one component, and then you could have another component, but you don't have the third component, unfortunately. So there's other ways to get at the third component. With GPS, you have all three. So this is always an issue. How do we interpret the interferograms and put them into maybe northeast and up deformation, something that we'd like. Anne said there's this textbook coming out soon, and actually there's a preprint version online. We'll send you the link to that so you can look at the book. It's basically the same as the printed version that's coming, and it's free, open. And if you go through that book, or you are attentive throughout this 3 days, you should be able to answer these 16 questions about SAR and InSAR and time series and things like that. So these are sort of the objectives of the textbook, what you can learn from that book. Okay, so in this conclusion of this short section, the atmosphere is very transparent to microwaves. That's why it's a good place to do satellite remote sensing. I didn't talk about this, but the amplitude of the SAR images depends on roughness of the surface and the slope of the surface and the dielectric constant. We won't really talk much about amplitude of the radar image, but we'll focus mainly on the phase, and the phase depends on the line of sight deformation in the surface, or can depend on the topography, depending on what you want to do and how you arrange your satellite orbits. InSAR products include wrapped phase, coherence, and line of sight displacement. That's after you unwrap the phase. You can make line of sight displacement. Phase unwrapping, we'll talk a lot about that because it's a challenge and almost an art form, but it's really important. And most processing is done in radar coordinates and then transformed at the end to geographic coordinates. But again, I said before that may be the old-fashioned way of doing it. With NISAR, we may go to geocoded SLCs. So here are the instructors. You saw this slide before. And if you're taking the class to and participate in the breakout sessions, these will be instructors. Hopefully you've all communicated with them, or they've sent you an email. And mainly what you'll be doing is preparing to give a presentation at the end, a short presentation. But also we have this set of homeworks, and even if you don't have an instructor, it would be useful to go through these homeworks, and you could learn InSAR processing and GMTSAR on your own. So the first homework is just learn Unix, learn how to use Unix, and that's a challenge in itself, and learn how to use a text editor and so on. So the second part of the homework is to learn something about generic mapping tools. There's a UNAVCO course on this, but you can go through the tutorials and learn enough GMT to do GMTSAR. You don't have to know all the details of GMT to do GMTSAR. One thing I like to stress is a lot of times people get hung up. There's a file called .cshrc or bashrc or tcshrc. So when you log in, this file gets executed, and you should try to understand this file. This is part of the Unix part, and I think this is one from Eric Lindsay from many, many years ago. But you really need to understand this, so when you type a command, you'll know, oh yeah, the command is over there and it's going to run. But if you don't understand it, you can get really hung up. Homework 3 is to learn GMTSAR, install it, install Google Earth, maybe read some of the literature on this. And then the homework 4 is more to learn about SAR data access. How do you download data sets and arrange them on your computer and make a digital elevation model that you'll need to do the processing and so on. Homework 5 is something on Jupyter Notebooks that's just coming along. But I think that's the future of all this. Okay, so these are the learning objectives from the GMTSAR site at EarthScope. And again, you want to learn how to use Unix, And you'll also have to learn how to use a package manager, something like Homebrew, depending on the computer you're on. Gather topography grid and make a basic map. We used to have this as one of the assignments, but it's a good thing. Make a topographic map of where you live. Understand the basic physical principles of SAR and InSAR. Learn how to generate interferograms with test data sets that are already available. We'll show you where those are. Make your own interferograms of something you're interested. And finally, if you really are advanced and have a lot of computing power and time, how to construct InSAR time series with Sentinel-1 data. So I'm going to stop there. It was all sort of fast, but again, you'll see all of this again later on in the course. So stop sharing.
Yeah, and our next session is an introduction of the GMTSAR, so a software that can be used to generate those InSAR data product that David just mentioned, the wrapped interferogram, the unwrapped interferogram, the phase coherence, and sometimes when you do surface deformation analysis, a software that generate a stack of interferogram that will be usually used as input data for surface deformation analysis. The instructor was the Xiaohua Xu, who spent a lot of time in develop the current GMTSAR version. Because of the time difference, he is currently in China, also running a companion GMTSAR short course in person in China. So he made a recording that I'm gonna play. Let me find that. Share the screen. So everyone can see it, right? So I'm gonna start playing the recording.
Hi, everyone. This is Xiaohua Xu from University of Science and Technology of China. Today, I will be giving a brief introduction to the GMTSAR software. To start with this part, I'll be beginning with a brief history of GMTSAR, how the software came into being. And then I'm going to give you guys a brief introduction to the design of GMTSAR, like how the software is composed of. I'm going to introduce you guys to some of the recent developments and some of the supported missions, and I'm going to give you guys some examples later on. So around the year 2000, David Sandwell started to put together a series of packages in order to process SAR data. That includes a SAR processor from Howard Zebker, which was rewritten by Evelyn Price later on, and also the precise orbit modules from Remco Sherrill from Delft University. And also the post-processing part were dealt with the GIB software developed at MIT. Then around the year 2010, the GIB software was replaced by GMT, and thus the software is being called GMTSAR. Later on, there are more developments, such as different processors for different satellites by Matt and Rob, and also two-pass processing modules by Xiaopeng. But what really makes GMTSAR like today's GMTSAR is when Paul was on his sabbatical, and he helped wrote GMT to be able to handle large binary tables. And he also rewrote the interfaces in GMTSAR to call GMT modules directly in the C code. And later on, there comes more developments. The development of the software was not only about the code development, but Paul also taught us how to manage software. Back in 2014 still, we were actually still using these package releases through our website. There's a link on the webpage, and if you click, it will provide you a package. But really on the server, there are like a series of packages. And specifically on any of these versions, there are actually more packages. Paul sort of convinced us that this is a terrible idea and we should start using subversion control systems. So we actually migrated our developments onto the Hawaii server, where we have a web page of the software, and also we have this wiki to tell you how to install the software. We also have a forum there to interact with the users, help them address issues. Then in around like 2018, again, it was the GMT team that sort of convinced us that GitHub is a better way. It will allow multiple development at the same time, and it is free to use. So we moved everything to GitHub. So as you may know, our development team actually maintains a pretty close relationship with Team GMT. The two teams have quite some interactions. Since we use GMT for all the post-processing, we usually just bug them when anything related to GMT goes wrong. And of course, we do provide a lot of feedbacks, and by extensively calling modules that are not commonly used for plotting, such as computation with grids, data manipulation, and so on and so on. Plus, we are also on each other's steering committees, trying to provide suggestions on like how the software develops. I am currently on the GMT steering committee, and Paul was on ours, and we are also actively looking for a replacement since Paul left us. Another type of interaction is that we constantly exchange gifts, mostly us bugging the GMT team for coasters and stickers. And feedback that we provide is when we run out. Another important part that we learned from Team GMT is that getting a usable software is actually relatively easy, but building a user community takes a lot more time. The GMT folks actually maintains a pretty great forum where they can interact with the users. Currently, we are also using our GitHub page to do similar stuff. So if you have any issues or meet any problems using the software, feel free to leave anything under the discussion panel or under the issue pages. An alternative way to interact with users or getting new users is by hosting these short training courses that you are in right now. So under the sponsorship of UNACO, or by now it's called EarthScope, we've been doing that for over a decade now. I think it's 14 years now. It started around 2011 at Scripps, and then that's 2013 at UNACO. Then in 2015, I joined the instructing team. You can also see some of the GMT folks there. Then the COVID came and everything became online and remained online afterwards. And earlier last year and this year, we are actually hosting these kind of short courses in China as well. You can also see GMT team members there. But it's not just about GMTSAR. We actually incorporated more stuff. Here's a bit more on the development of our team members. As for the developers, when GMTSAR was first started, there were essentially 5 of them. Paul was there too. During the past number of years, we started to bring more members or younger members onto our team. That's actually the starting for. And then I joined. Then a lot more of us joined, and many of them will be your instructors during the breakout sessions. And we also brought some more people from like China and also Europe. And also we have Melissa, who's been supporting us for a very long period of time already. So I'd like also to go through a little bit of the current status of our software. Here are some of the past and current funding support, like from NSF Geoinformatics, Cyber Infrastructure, and also CSSI, and also SCEC. Some of the recent developments, we will support InSAR for sure, and also we've been developing Python modules as we figured out that the newer generation doesn't like C shells very much. We just published a new book on InSAR theory, and a pure tutorial book is on its way, and the documentation page is already there. As for some of the metrics, since 2013, we've had a big surge of user increase. What's shown here are the total and unique clones every 2 weeks. Yet the number of issues are actually dropping quite a bit. That doesn't mean that our software is getting perfect, but instead, we're actually finding an alternative way to respond to users' feedback. That is by hosting group chats. It is a little bit more immediate and quite interactive. I mean, these are 2 group chats in China right now. They sum up to total around 1,000 users. On the aspect of mission support, here's a figure with past and some of the future missions. You may recognize some of them, like ERS or NVSAT, and also ALOS or Cosmos ScanMat, and Sentinel, and so on and so on. And in the future, we'll be supporting like NISAR and also Biomass maybe, and also Lutan, which is Chinese L-band satellite. So next, I'm gonna go through more details about the software itself. So overall, GMTSAR is an open source InSAR processing software. It has the capabilities of handling most of the open SAR data, from like processing a pairs or interferogram, or doing large stacks of interferograms using linear parallel, it has tools to do time series with an atmospheric correction module as well. But most importantly, it is completely free and open. That means anyone, regardless of the purpose, could take any piece of the software for like academic or personal or even commercial uses. You can copy it, modify it, or redistribute it. We don't have really any limitations on it. It is written in C for most of processing modules and C# for connecting them together. We promise that there will be Python modules in the future to replace the C# scripts. The product of GMTSAR is, in fact, fully compatible with GMT for immediate use to produce publication quality figures, which makes things really easy to handle if you are already familiar with GMT, of course. Or in other words, since GMT is already a pretty popular software for plotting Earth science data or geomaps, if you're an advanced user of GMT, you could easily manipulate the product from GMTSAR using any of the modules in GMT. And lastly, we try to make our processing chain as simple as possible so that if you're a beginner in SAR, you should be able to learn all the processing theory just by looking at the code or scripts. Everything's pretty much linear there. And if you're an advanced user, it should be simple enough for you to modify or implement your own stuff into the InSAR processing chain with the GMTSAR software. Okay, here's a diagram of the design of GMTSAR. The entire processing chain is divided into 6 steps. We're going to go over them one by one. So the very first step is called pre-processing. The objective for this step is to convert the incoming data from different space agencies into a format that can be recognized by the software, which is a generic format for the software. This is the part where actually the software differs the most from one satellite to another. If every agency could agree on a common format, that would be great, but it rarely happens. Anyways, this step actually converts all the incoming data into several like files, that is the raw file or SLC file. In other words, raw radar echoes or the focused single look complex images, and also the PRM, which is the parameter file, and also LED, which is the orbit file. The associated modules are usually called with the satellite name underscore preprog. The second step is called focusing and alignment. Focusing is in fact the step to convert the raw radar echoes into SLC. Nowadays, many satellite agencies has taken this part as their job. So sometimes when you get the data, it's already focused. And next, it will be to align these radar images together. So each time the satellite observes the ground, their footprint actually are slightly off. Like if your satellite is slightly higher or lower, or tilted a little bit forward or backward, then the coverage on the ground may differ a little bit. So the alignment step actually ensures that after characterization, the images are actually mirroring the same target on the Earth surface from one pixel to another. So they match together sort of perfectly. The third step is called back geocoding. It is a step to project the topographic information from geo coordinates into radar coordinates. And later on, you can use this information to do interferometry. And sometimes this part could be a little bit slow, depending on the interpolation approach you're using or how large of an area you're performing this back geocoding. Then you pretty much have everything to do interferometry, which is basically interfering to radar images. You can later filter and smooth your face to reduce noise. The theory will be covered later, so I won't talk too much over here. And once you have the interferograms, you can unwrap them. Phase unwrapping is to sort of connecting all the fringes from interferogram together to produce the continuous phase map. This is sort of necessary if you want to measure deformation. It is more like an art sometimes, and this will be covered later on. And lastly, you can geocode your product. The information used for geocoding is actually from step 3, back geocoding. Basically, we produce a large lookup table used to interpolate the data in radar coordinates into geo coordinates. And the main script here is called proj RA2LL. Or higher level script is called geocode.csh. Okay, some more stuffs. Other than the processing chain itself, we have some modules or scripts outside the standard processing, like we have modules to do all kinds of corrections, such as a tide correction or an ionosphere correction. We also have some time series tools where you can use coherence-based SBAS to produce a time series. We have some data manipulation tools as well. You can cut, paste, or reassemble the burst. Many of them are actually used for processing the Sentinel-1 TOPS data. And lastly, we have these what we call the top-level scripts, which are used the most, I think. They basically cause the modules mentioned above to finish the processing. And if you have tried some of the example data set, you probably have noticed that this P2P processing.C shell is almost in every one of them. We do have some other like top-level scripts to deal with frame-wise processing, such as for Sentinel data or for ALOS2 data. But in fact, inside of them, they are actually just calling this P2P processing again and again. And inside this P2P processing, it is actually composed of these 6 parts. You can use a config file to control like which part you want to run and which part you want to skip. And by playing with this P2P processing, you can deassemble and reassemble the processing chains in order to do, for example, batch processing to deal with, for example, a large stack of data. And this will be covered later by the lectures. And here are some of the recent progress of GMTSAR. Most of them are from recent years, past a few years maybe. So I'm not going to go through any of the details of these developments, but most importantly, what we would like you guys to know is that please don't hesitate to open an issue on our GitHub page. If you would like to request a new feature or you find something that is not appropriate, or if you would like to help us build any of the modules, that would be great. And here are some of the example products you can get with the GMTSAR software, such as radar phase. This is actually the interferogram of the Ridgecrest earthquakes in 2019. And also you can calculate phase gradient using the GMTSAR software. You only need to turn on it in the config file. You could also do MAI processing. This is again for the Ridgecrest events using ALOS2 ScanSAR data. You can see some of the ionosphere perturbations in these results. You could also run burst overlap interferometry by getting all the double difference phase from the burst overlap area using the TOPS data. This is again for the Ridgecrest earthquakes. You may also run pixel offset tracking using the GMTSAR software. This is actually a pretty recent event for the big earthquake in Myanmar. These are actually using the TOPS data running cross correlation, and you can get all these offsets from the faults. A little bit more examples. Most of these are associated with the ionosphere correction modules. You could do that for ALOS data or ALOS2 data. You can also work with Sentinel data here as well. Left-hand side are phase, in the middle are estimated ionosphere phase, and on the right-hand side are the corrected ones. Then at the very end, I would like to end the introduction with this plot. This is actually the number of maximum acquisitions you can get from open data. We are only counting the ERS, NVSAT, ALOS, and Sentinel, and potentially future NISAR missions. This is actually a time when my PhD advisor, David Sandoval, started working with InSAR. That's at the area of ERS. This is when I started working with InSAR data. That's when all of these open missions are dead. But if you start to join right now, you are pretty much at a historic high. So the field of InSAR is actually prospering, and this is the right time to join. And that's pretty much all of my presentations. Feel free to drop any questions. Thanks.
Yeah. So I would thank Xiaohua for making a great recording. David, do you want to have a short comment on that?
No, that was a nice summary he did. Yeah, they have another workshop going on in China right now at USTC. I think this is the same week. So it's too bad he can't be here, but he's running that workshop.
Yeah, and I want to also comment that I joined the GMTSAR fairly late, but I'm really fortunate to be in this team. And I have been working with a group of young core GMTSAR developer, and we are trying to expand the team. So there are already some current planned activities to further improve GMTSAR. So I want to give a quick comments on the directions, and you're very welcome to drop us an email about what you need, and so that we hopefully can take into consideration in the future development. So right now, one of the major efforts we are trying to do is to try to make the GMTSAR more user friendly. So you can see there are many different processing steps. As a user base expand, most of them might not care about all those small details. So we hopefully to redesign the processing chain so that it's going to make it easier for users to interact with the GMTSAR and get a geocoded interferogram, as those radar coordinates is more intuitive for radar expert, but they are not easy to work with, necessary for a broader user base. So we hope to be able to readily develop those topography corrected interferogram in the lat long direction. So that's one of the major steps we are planning to do in near future. And also we have been already trying to working on replace some of the seashell script to Python script. So we will have a companion GMTSAR version of the current GMTSAR software. And so another thing we believe the team, like Eric and Kathleen, we have talked about this, we decided to do is that in the past, people has been like, you learn GMTSAR, then you use GMTSAR to process data, and you learn other software, you start to only exclusively use that. But the idea is the same data, and the interferogram generated from those different software should be actually comparable quality. So another effort we would like to do is to provide some of a more utility software so that the GMTSAR can be more compatible to more maybe community-wide with other software like MinPy, so that people don't have to, like they can kind of take advantage of the new advancement from each of the team and be able to use them in more creative ways. So that's kind of the three efforts we agreed, and we are going to focus on in the near future. And of course, when NISAR come, we are committed to support the use of NISAR and be able to integrate those capability to process and now analyze data, NISAR data using GMTSAR. So that's the comment I have. And so next, we are going to have Catherine Materna to talk about SAR theory. Catherine.
Did we want to have a break, a short break, or no?
Yes, I think we can maybe have a 5 minutes break and start at 11 a.m. Austin time, at 4 minutes.
Okay, thanks. Yeah.
Yes. Okay, great. Hello, everybody. My name is Catherine Materna. I'm very happy to be here with you guys today. I took the GMTSAR short course in 2016. And today I'm going to share with you our first lecture on SAR theory. And by the end of this lecture, you will hopefully have a better understanding of some key questions, such as why do SAR satellites look the way they do? Why are they in the orbit that they are? Why do they look off to the side? So we're going to cover that today, as well as other information you need to know about how SAR works. For a little bit more, if you want to dig deeper into this topic, many of the figures here come from this chapter, I forget it, maybe chapter 2 of this, the textbook that was mentioned in Xiaohua's talk. So SAR satellites like Sentinel-1 look something like this, maybe 10-ish meters across, and by the end of this lecture, you'll have an understanding of why they have to look like this. So the underlying theory begins with the familiar concept, perhaps, of echolocation. How SAR works depends on the idea that the satellite emits a signal, which bounces off of a reflector on the surface, and the reflection returns back to the sensor and is detected at a given time, t. So just like echolocation, the satellite is basically listening for an echo at a time t. It's more complicated than that, as we'll get into in a few slides. The satellite is looking for objects on the ground based on the time that they return, such as here, where is this ship? Well, where it is depends on the time t that the signal is returned back to the sensor. The satellite is emitting, in fact, a beam. So we have to ask the question, how do we form a beam? Well, the satellite emits a pulse of electromagnetic radiation in the radar frequency. So it has highs and lows, like sinusoidal, and the wave field begins to look like this. As the satellite continues to emit this beam, continues to emit these waves, a beam is formed as the satellite moves. So this is the constructive interference of a number of emitted pulses. And as you can see, the beam gets narrower and more formed as more pulses are put together. So we're going to explore this concept a little bit more quantitatively. The basic idea of a satellite emitting a beam is that the area illuminated on the ground and the satellite in the sky, they follow the same physics as the single slit diffraction experiment in classic physics. So if you've seen this before, a plane wave incident on a slit and a screen in the far field produce an interference pattern or diffraction pattern on the far field where the amplitudes constructively interfere in the middle of the diffraction pattern, and at a certain place across the screen, they destructively interfere, and you have a zero. The location of the first zero crossing is given by the ratio of the wavelength of light to the size of the slit. So, for example, this is the amplitude pattern on the screen in the far field. And the first zero crossing occurs at an angle theta, where sine of theta is lambda over L. L is the length of the aperture. The reason this applies to satellite interferometry, or SAR in general, synthetic aperture radar, is that the resolution on the ground, so we're going to talk a lot about the resolution of pixels on the ground today. The resolution of a pixel on the ground is given by the area between the two zero crossings. So the resolution of the pixel on the ground depends on the ratio of the wavelength to the size of the aperture. If you're working in, let's apply this a little bit. If we're working in the optical wavelengths, and let's say you have a satellite up in space, and the length of the antenna, or the length of the aperture in this single slit diffraction experiment, or L, all of these are used interchangeably. The length of the antenna, let's say it's 1 meter. In optical, the wavelength is 500 nanometers, for example, in the middle of the visible spectrum. And if the satellite is 800 kilometers above the ground in low Earth orbit, we have a calculated resolution on the ground of 0.8 meters. So the size of this beam here, which is the size, the distance between the two zero crossings in the single slit diffraction experiment, is about 1 meter, on the order of 1 meter, and that's our pixel size. So in the world of optical sensing with a 1 meter antenna, this pixel size is actually quite small. And so we can take high resolution images from space in the optical band. However, if we try this same calculation in the microwave band, and let's say for the sake of argument that we have a much larger antenna, like a 10 meter antenna, but let's say we're in the microwave band with 0.23 meters or 23 centimeter wavelength, this calculation gives us that the ground resolution of our sensor is 46,000 meters. That's the size of 1 pixel, and that is not good for any sort of sensing that we want to do. If 1 pixel was 46 kilometers by 46 kilometers, there's very little imaging we could do. And that's simply because the wavelength is large compared to the antenna. So how synthetic aperture radar gets around this is a bit of a trick that I'll introduce in the next few slides. But first, we need to go over the coordinate system that we're going to use to understand how SAR works. So the coordinate system looks something like this. You may see this more in the short course. The satellite is flying in a certain direction, and we call that a long track. This is the antenna, or the aperture, or L. And in the direction that the satellite is flying, we call this direction the azimuth. That is one of the coordinates in the coordinate system. And then the other direction, off to the side, we call the range. So this coordinate system, azimuth and range, is very fundamental in SAR imaging. It's not the same as north and east. It is a long track and a cross track. So you'll hear these words azimuth and range a lot. So let's go into how we improve the resolution of SAR sensing platform in both azimuth and range. First, we'll start with azimuth. How do we get better than 46,000 meters for a pixel size? Well, the key idea is that as the radar flies overhead, it illuminates each point on the ground for an extended distance. And we can cleverly combine all the information in phase over that distance and use it to synthesize a synthetic aperture as though the sensing aperture were as long as the entire distance that that pixel is in view. So we carefully combine the data from several antennas at different locations as it's flying, and the result acts as if it were a single giant antenna. So let's look at the math just a little bit. What happens if instead of L as our antenna length, instead of L, we could illuminate the ground with the entirety of the space across the sky that the pixel that our target is being illuminated? So as we talked about with a real aperture, RA, the size of the real aperture is given by the height times lambda over L. And as I said, this is tens of kilometers for radar and very, very poor. But what if we could use this distance here, 2 times the real aperture, as the synthetic aperture? And if we plug this into the equations here, we put 2RA, which we get from the geometry of this sort of problem, we actually, when we plug this in, we find that the ground, that the resolution on the ground, or the size of a pixel, turns out to be L over 2. And this is very surprising because it's independent of the wavelength, and it gets better with a smaller L. So this is the size of the actual satellite. And if we could cleverly combine all this information in phase, this our ground resolution, doesn't matter how far you are, doesn't matter the wavelength, the ground resolution is related to the size of the antenna, and that is it. So that's our theoretical best ground resolution in azimuth, L over 2. The process of going from a real aperture to a synthetic aperture is called focusing, and we'll talk about that in a couple of slides. So to summarize, the theoretical azimuth resolution, L over 2, is something that we would like to see because it gives us a small ground resolution, but it can only be achieved if the radar is flying fast enough to distinguish one pixel from another, and it does that by seeing a Doppler shift. And it can only be achieved if the radar is pulsing the that beam that it's sending out fast enough to measure that Doppler shift. So there's a little bit of a, we have an engineering trade-off here. We want to achieve high resolution of something like L over 2, but we need to be moving fast enough to track a Doppler shift, and we need to be pulsing fast enough to see that Doppler shift. So the phase change between consecutive pulses must not exceed 2 pi, or we will alias. So next, we've got the Doppler shift goes from high frequency is blue shifted, low frequency is red shifted, and as the satellite moves across the sky, it sees a target pixel first blue shifted as it moves towards it, and later red shifted as it moves away. So let's talk about range. Range is actually completely different from azimuth, and we need another trick in terms of synthetic aperture to create higher resolution in the range direction. And this is why the satellite must be looking off to the side. And the trick here has to do with something called a chirp. So let's say we want to distinguish pixels along the ground in the range direction. The way that we would do this in a, let's say we theoretically had everything we ever wanted in the world, we would emit a very short pulse. And that short pulse going out in all directions here would hit off of each target on the ground and return back and because it was such a short pulse, the arrival time of that pulse can be very precisely determined, and therefore the distance to the targets can be precisely determined, so we can construct an image. We would want a narrower pulse to achieve this fine range resolution. That would allow different pixels to arrive at separably different times. However, we have a problem here, which is that to send a signal to the ground, this is the amplitude of the returned signal, the sent out signal, the amplitude of the returned signal. The problem is the energy that we send out attenuates with r squared from the source. When it hits the ground, it will attenuate with r squared back. So it will attenuate with r to the fourth. And in order to get a narrow pulse sent to the ground and reflected back to the satellite, we would need so much power from this antenna that it would be prohibitive. So we need another trick. How can we make a narrow pulse without sending out way too much power? Well, the answer is instead of sending out a pulse, the satellite sends out a chirp, which is a sweep of frequencies from low frequency to high frequency. You can see here in the time domain, it starts at a low frequency and finishes at high frequency. In the frequency domain, it sweeps from a V1 to a V2, sweeps up like this. And the set of frequencies that are spanned by the chirp is called the bandwidth. As it turns out, the bandwidth can be related to the slant resolution because the larger it sweeps, the more the sensor on the return side can distinguish one pixel from another by catching different chirps as they return. So the slant range resolution is determined by the bandwidth, the max frequency minus the minimum frequency, and the speed of light, and the 2 is for the two-way travel distance. So this is the resolution in range, specifically in slant range. So let's talk about a particular satellite. Sentinel-1, let's say it has a bandwidth of about 100 megahertz. What is the effective pulse width, and what is the slant range resolution? So the pulse width is this term. The slant range resolution is divided by 2 because it has to go there and back. And if you do this math, c being the speed of light, you find that the resolution is actually, the effective pulse width is 3 meters, and the slant range resolution is half of that, or 1.5 meters. So you can have a really fine range resolution by using a large sweep across the frequency spectrum. So if we look at this a little bit geometrically, what I was describing here is the slant range resolution, this being the slant here, but we kind of want to know the ground range resolution because that's where our targets, our pixels are on the ground. And so the geometric relationship between these has to do with the incidence angle here. So to convert between resolution in slant range and resolution in the ground, resolution in slant range will be a little bit higher, and in the ground it'll be a little bit lower. We divide by the sine of the angle. And the incidence angle, as you will see over and over again in this course, the incidence angle is always measured from the vertical. What this means is that in the near range, which is this part here, you actually have less resolution. And in the far range, you have more resolution. Yeah, poorer resolution in the near range, better resolution in the far range. You can think of this actually makes a lot of sense because what the antenna is looking for when it returns, when the pulse is returned, is the ability to separate between different pixels. And if there's a larger travel distance that needs to be traveled, these pixels will separate and their chirps, the reflected chirps, will separate a little bit more. So you have better resolution in the far range. So let's put all of that together. There's two different ways geometrically. There's two different ways to look at how the synthetic aperture radar works as a whole system. So one of them is this geometry model where we can see that the satellite is flying across its track And as that pixel is illuminated, as a certain target pixel is illuminated more and more, the pixels become more distinguished from each other, our resolution increases. So geometry, as the satellite is flying, a big aperture produces a smaller beam, just as the single slit diffraction experiment showed. There's also the Doppler model, which is that as the target pixel is first illuminated, we have a blue shifted reflected return. And as it is illuminated at the end, we have a red shifted or lower frequency return. And we can relate the return of this pixel by seeing the frequency of that return over time. So you see this here, the frequency changes over time as the satellite flies across, and the Doppler shift catches returns from that pixel. So this looks familiar, right? Because this is actually the exact same thing that the range resolution is using, the exact same trick that the range resolution is using, except we flip it because we have the high frequencies first and the low frequencies at the end. And so this is the exact same idea used in Azimuth that the Chirp is using in the range. And when you put all of this together, you end up with the ability to distinguish pixels on the ground in both azimuth and range at a much higher ground resolution than you would be able to achieve without using this synthetic aperture. I will briefly talk about the how fast do you pulse? Well, basically we have two limits. The first limit is we need to pulse fast enough to be able to see the entire Doppler shift. And you can math it out a little bit with the velocity of the satellite, but we're going to speed through this today. So pulsing faster means you can catch more of that frequency shift due to the flying satellite, the Doppler introduced by the flying satellite. But we have an upper limit too. We can't pulse infinitely fast because we need to return all of the EM waves that have come from both the near range and the far range need to return to the satellite before we can pulse again. So there's an upper bound, there's a lower bound on the pulse repetition frequency given by the Doppler. There's an upper bound on the pulse repetition frequency given by your geometry, how far you are from the ground. The return from the far range must come back before you pulse again. And so there's this narrow range of pulse repetition frequencies that we can use. And so the point I want to get across is that in summary, SAR in general is like a Goldilocks machine. It needs to be moving at just the right velocity. It needs to have just the right pulse repetition frequency. The power requirements need to be right. For the bandwidth, the range resolution and the azimuth resolution, they all play into the design of the system. And each of these things need to be just about right in order for the system to work. Next, when all of that jumbled information from all the pixels is returned, there needs to be a process called focusing. The phase from a reflector starts out as a hyperbola, and it can be focused into the original pixel where it came from through this process. And so it's exactly the same as a time migration. If you're familiar with seismic imaging, you identify hyperbola basically in the space and find the reflector on which they originated. And so here's an example of unfocused raw data, as we would call it, and then it is compressed or focused in the range and then in the azimuth. So we have a bright reflection from a corner cube, and it's somewhere in this unfocused data. When it's compressed in the range, you start to see that it's at that there are these corner cube reflectors at certain locations, but it still needs to be compressed in azimuth. And when it is done, you have these really bright reflectors that have been identified from that original unfocused image. SAR gives us typical image resolutions through the magic of the Chirp and the Doppler shift, and the synthetic aperture. We have range resolutions and azimuth resolutions, typical resolutions of about 10 meters. And it gives us images of the ground with this degree of resolution. The image itself contains backscatter from a range of sources. So sources with roughness on the order of the scale of the wavelength return bright reflections to the satellite. Sources with vegetation, you can have multiple reflections off of all sorts of reflectors within a pixel, and that includes the tree trunks, the tree branches, the leaves. How a radar reflects off of these signals depends on the wavelength. Backscatter can have bright days and less bright days depending on what's in the backscatter image. And so this is a part of the image that we would call the amplitude. Bright reflectors return a lot of energy back, so the amplitude is very high. And when conditions change, windy weather, flooded conditions, you can have changes in the backscatter amplitude. Of course, what we're doing here in this course is the interferometric part. So we're mostly focused on the phase, but I did just want to point out that the amplitude can be useful for certain applications. One other thing about SAR is that if your surface is not flat, you can have something that looks a little distorted, like these mountains here. They look like they're tilted over to one side compared to the way we expect mountains to be. And this is because of something called the layover effect, where basically where the pixel is depends on the time at which the reflection returned to the sensor. However, if there's a steep slope, the reflection comes not off of the expected ground, but off of a higher point. It returns sooner than the satellite expected it to because it's closer in this line of sight, and that makes it look distorted. So we can partially correct for these effects if we have a digital elevation model in geocoding, but sometimes the layover effect is actually quite difficult to correct for. So in short, reflections that occur too soon can sometimes appear in the wrong place. Similarly, one other trick about radar is if you're illuminating an object that happens to be moving, the object in the returned image can appear displaced. And this is because the SAR is using the Doppler shift to form and focus the image. So if this object has the wrong type of Doppler shift, because it is moving itself, it can appear in the wrong place. So here's an example of a train track, and the train was imaged during this pass of the satellite, and it appears offset from the train track. Lastly, I just want to point out that the wavelengths that we most commonly use for SAR are L-band, maybe S-band as an ISAR is launched soon, C-band, and X-band. Don't worry if these are hard to remember. They're sort of they're intentionally confusing, but basically L-band, we typically use 24 centimeter wavelength, C-band, typically 5.6 centimeter wavelength, and X-band is around 3 centimeters. So these are the scales of objects on which these wavelengths reflect the strongest. And with that, I think I'll end here.
Thank you, Catherine. And our next section is for David to talk about orbits.
Thanks, Catherine. That was great. The Goldilocks, we have to have the sensor with just the right attributes to get SAR imagery. And so I'm going to talk a little bit about orbits and, I have to share my screen. Share. And orbits are really important for doing SAR and InSAR, and it's a little bit boring, but it's required because in order to measure some displacement on the ground between two satellite passes, we have to know exactly where the satellite is to that same accuracy. So there's two measurements involved. One is this range, and one is the satellite orbit. And the orbit is also used for other things in SAR. So I'm going to review some of that. This is a chapter in that textbook we've been talking about, and it talks about Kepler elements, and I'll briefly go through that. You don't really need to know that, but you need to know something about how to get very precise orbit information when you process the data, and we'll talk a lot about that. So here is the ground track of a particular satellite called Sentinel-1. And all these SAR satellites are in similar types of orbits. They're at high inclination that we won't get into, but in other words, they cover most of the Earth, this one up to 80 degrees north. And they're in retrograde orbits. So the path of the orbit, hope you can see my mouse, the ascending track goes from southeast to northwest, and the descending track goes from northeast to southwest, and the Earth is spinning, of course, in a prograde direction. So the orbit's opposite of the Earth rotation, and that's done for a purpose to get it into the right, to have the right precession of the orbit plane. We won't get into that. But to do InSAR, you have to have the orbit repeat exactly between the reference and the repeat image of the Earth. So, and exactly means better than 100 meters if you can do that. And so all these orbits have a particular repeat cycle. Sentinel has a repeat cycle of 12 days. And in that 12 days, it does 175 orbits. Other satellites maybe have 35-day repeat or 42-day repeat, but they all repeat and explain what governs that repeat cycle. So why do we need orbits? Well, as Catherine just discussed, we need to focus our SAR image by assembling all the radar echoes along this flight path. And we also have to know the range to that point reflector on the ground to about a quarter of the wavelength of the SAR. So we have to know the range really accurately, a few centimeters. So to focus the image, we need to know where the satellite's going, how fast it's going. So that's really important. Also, we'll want to take our data that are in radar coordinates and transform into geographic coordinates, and that should be a 2. And that involves the orbit and the topography of the Earth. To align the images, the reference and repeat images have to be aligned very accurately to a fraction of a pixel, and Eric will talk about this. We need good orbits. And then finally, when we make an interferogram, if there's an error in the orbit, it will appear as an error in the interferogram, just a direct one-to-one mapping. So it's good to have very precise orbits for these 4 reasons. And we'll talk a little bit about how we do this mapping from geographic to radar coordinates, but it's basically just a computer algorithm. Okay, a little background here. There's really 2 types of orbits that people use for the Earth. One is called a near polar orbit. In other words, it has an inclination that brings it towards the poles more. They don't go exactly over the poles. And the inclination is this angle between the equator and the satellite track. These orbit they're between 400 and 1,500 kilometers high. You can't really go outside of those bounds. It orbits about 14 times a day. You really can't change that number very much. So that's a typical SAR. Any kind of remote sensing satellite is in that kind of an orbit. And then we have these high orbits, geosynchronous orbits, and they have an orbit period that's exactly 1 day. So the satellite appears to hover over top of where you are on the Earth, and this is good for doing real-time weather monitoring and also communications. So we're going to deal mainly with these near polar orbits. What are the basics here? Why does the satellite stay in orbit? Why doesn't it just fall back to the Earth? Well, we have 2 forces that are acting on this satellite. Here's the Earth. This is not really drawn to scale. The actual orbit is way down here, but so we have this mass orbiting the Earth, and the mass of the Earth and the mass of the satellite cause a gravitational attraction that wants to pull the satellite this way. But the centrifugal force of the satellite moving in a circle around the Earth is outward, and those have to be balanced exactly, or the satellite would crash into the Earth or go off into space. And so that's the basics. And most of these remote sensing satellites are in pretty much circular orbits. And given that range of altitudes, a typical altitude is 700 kilometers. Almost all the InSAR satellites are at 700 kilometers altitude. The ground track speed is 7 kilometers per second. You can't change that number. We're stuck with that. So when Catherine talked about sampling rate, there was a velocity in there, and this velocity is pretty much fixed. So we can't change the sampling rate of these SAR satellites. They all have to be 1,000 or 2,000 times per second. That's what it is down here. Yeah, say 1,400 times per second. Okay, there's two ways to describe orbits. One way is to use these things called Kepler elements, and I'll briefly discuss them, but you don't need to know this when you're processing InSAR data. And this involves knowing things like, here's the Earth, here's the satellite, there's an angle between the satellite and the Earth. Most of these orbits are elliptical, so they have an apogee and a perigee. And these numbers, 3 of these numbers here are 3 numbers of the Kepler elements. And then you have to take the satellite orbit and put it into an inclined orbital plane around the Earth. Here's the center of the Earth, here's the orbit, and there's other angles here, the argument of perigee, this angle between when it crossed the equator and when it was closest to the Earth, perigee, and then there's the longitude of the node, another angle. And these 6 numbers or elements make up the Kepler elements, and they're used to describe where the satellite is at any particular time. But having said that, we don't really use these. We're going to use a different way of prescribing the orbits. I'll get to that in a minute. But here's a demonstration of a retrograde orbit going around the Earth. The Earth's turning underneath the satellite. So we have the ascending track going from southeast to northwest. And on the other side of the Earth, there would be a descending track going from northeast to southwest. If you look at this on the ground, you can create a ground track. It's actually an exercise in the book that's sort of fun to do. You can code this in MATLAB, but you can put in the satellite orbit parameters like its inclination and its altitude and the rotation of the Earth and create one of these ground track maps. This happens to be Landsat ground track, and it orbits the Earth once every 16 days. And it looks like there's 232 orbits in that 16 days. So that's one particular ground track for this optical remote sensing satellite. But the SAR, again, this is a retrograde orbit. SAR satellites are very similar orbits. It even gets crowded up there in orbit because they all want to be in the same inclination and the same altitude. And so to avoid collisions, nowadays, all these satellites have to be brought back out of orbit when they get old. They have to be brought back to the Earth. Okay, so as I said a minute ago, you could use Kepler elements to describe the orbits, but those are only accurate to tens of meters or so. We really need to get orbits that are accurate to like 3 centimeters to do Sentinel-1 processing especially. And that is done using a different type of orbit description. These are called state vectors, and they're basically just time, position, x, y, z in meters relative to a fixed Earth coordinate system, x, y, z. And then we need the velocity x, velocity y, velocity z. So when you get any kind of SAR data, you'll also get this orbit file. And this is required. You can't do anything without this file. And you'll learn how to download Sentinel data, but then you'll have to learn how to download the orbit files that match that data set. And these files are called LED files. You'll see them in all the GMTSAR processing. You need an LED file, and that comes, it'll look just like this. If you view it, it'll look like this. So it's pretty straightforward. That file has to be a little bit longer in time than the time of the overpass. You need some endpoints there to do a real nice interpolation through the orbit. So as I said before, we need to use these orbits to focus the image and to map a point on the ground to from radar coordinates into lat long height, from lat long height into radar coordinates. So that's called back projection. And the algorithm for back projection is pretty simple, but it takes a lot of computer time because you have all these points on the ground, lat long height, and you have all these times along the orbit. And so you have to find the point where the satellite, if this is the point you're interested in, lat long height, you have to find the one that has the minimum distance between that and the satellite. That's called zero Doppler. In other words, that point is perpendicular to the velocity vector of the satellite. And this is usually done with just a brute force algorithm. You just put in, this is all done in Cartesian coordinates. You put in the XYZ of the point, the XYZ of the satellite, fly the satellite along here, find the minimum point, and do that for every point in the DEM. And you need a file to do that. Once you do that, you get this file. It's called trans.dat. It's a mapping from lat long height into radar coordinates. And this is really a second important file that you need in GMTSAR processing. The file just has in it lat long height, range azimuth. That's it. It's just 5 numbers. One other thing that we'll learn about later on is how to select data over a particular area. Let's say you're interested in California and you want to look at a descending track over this part of California, and you want to find it in the archive. Well, you have to know, the way the search goes is first you pick a small area and you find all the data that go over there, but then you want to find the one with the right track. What does this track number mean? That just means the number of orbits along this path here when they started counting. So the tracks can go from 1 to 175 for the Sentinels because there's 175 orbits in 12 days. So this is the 173rd orbit along that track. So you have to find all the data with the same track, and the search tools will let you put in the track number, or that's called the path number in most times. And then you have to do the frame, and the frame is the time along the track. Usually the time since the last ascending equator crossing. So tracks and frames are something you have to get used to, and it all depends on these kinds of orbits. So in conclusion, all SAR satellites are in these low Earth orbits at an altitude between 600 and 800 kilometers. You can't be much lower than 400 kilometers because you're in the atmosphere of the Earth, and you can't go out higher than this because you don't get much energy back from your radar as you go higher and higher. So this is the sweet spot of the orbital altitude. Given those numbers, and you plug that into that theory that I showed where you're balancing the gravity force and the centrifugal force, the ground track speed is going to be somewhere around 7,000 meters per second. Can't really change that number. These orbits repeat exactly for all these InSAR satellites. NVSat repeated at 35 days. ALOS-1 repeated, and ALOS-2 both repeat at 42 days. Sentinel-1 repeats every 12 days, but it's had in the past 2 satellites. I think there's 2 satellites now, so you can get data every 6 days sometimes. Depends if both satellites were operating. Accurate orbits greatly simplify the InSAR processing. In the old days, when we got started, we didn't have accurate orbits. So we had to sort of adjust and tweak the orbits to get our SAR image to look nice and to get our interferometry to look nice. But you don't have to do that anymore because these orbits are all very accurate, sometimes better than 10 centimeters. And it's used for proper focus, for transforming latitude, longitude, height into range and azimuth coordinates, this back projection, image alignment to subpixel accuracy, something that needs to be done very carefully, especially with Sentinel-1, but it now seems to work when you just put in the right orbits and get the data, things are aligned properly. And then finally, when you make your interferogram, you have to remove any kind of topographic phase, but you also have to, if you have an orbit error, you've got to correct for that somehow. And then these two files that are important, the LED file has the orbit in the Cartesian coordinates, and the trans.dat file has the mapping from lat, long, height into radar coordinates. So that's all about orbits. I probably went a little quickly, so maybe someone can have some more time, but yeah.
David, do you want to take a 10 minutes break, and then we can have the last two sessions today for InSAR theory and also the orbit mode, SAR acquisition mode?
Okay. I mean, the break was scheduled for after the theory, but
because there's only two sessions, so maybe the break right now, so each session.
okay. Yeah, that's good. Yeah.
Eric, does that sound good to you?
Sure. Yeah, that works for me.
Yeah, and I will bring back the break slides reminder so people can come back in time. So 10 minutes break.
Just a reminder to the instructors, there is the Q&A, and there's about 3 questions in there.
Oh, okay.
Yeah, there's been some good questions already. I answered a couple and some other people did too.
Oh. I can answer some while you're making your presentation, Eric.
Okay. Can you guys see that all right?
Yep, that's good.
Yes.
Okay, perfect. Oops. 1 second, set up my other screen. Okay, cool. So I'm going to kind of follow on from what Catherine and David were talking about with the SAR satellite and the SAR operations and orbits, and talk about InSAR. So this is kind of the chapter 5 from the book, if you've found that book download. So talking about interferometry and what are the components of an interferogram, and a little bit about how do we interpret it. So we'll get lots more on the interpretation and everything later, of course. So talk about forming an interferogram. What are all the different components of the phase? So we'll talk about Earth curvature, baseline, meaning the satellite orbits, the topography, phase noise, decorrelation, atmosphere, and then we'll talk about a little bit of the difference between some of the bands and how different satellites kind of function in terms of what they can recover. So the basic idea, I'm sure if you enrolled in this course, you're generally familiar with what an interferogram is, right? So it's the phase difference between two images. And so we call the raw SAR images SLCs. That stands for single look complex. So complex because it's got the amplitude and the phase information, so we can think of it like a complex number. Single look is kind of an outdated term that just means it's high resolution. Single look meaning no multi-looking, which is a sort of a downsampling or averaging. And so an interesting thing about the phase is that it's actually random. It's completely random. And this is what real SAR images look like if you just look at their phase. So most of the images that Catherine was showing, we were looking at the amplitudes. Those kind of make sense. But the phase values at every pixel are just going to be completely random. And that kind of makes sense because the roughness of the Earth is pretty large on the scale of the wavelength of the radar, which is like a few centimeters. And so at every pixel, you just kind of have a summation of all of the reflections off that pixel. And it's always going to end up with a slightly different phase. So the amplitude might vary systematically about, something about the brightness of the image, but there's not really any relationship with the phase. So it just looks like random numbers. But between two images, the key is that if our two images were collected carefully enough so that they're in kind of interferometric coherence with each other, if we subtract the two phases, then we see something like that. And you can see that there is a pattern. So this is actually just the mathematical subtraction of these two images in the phase. So this is what this looks like. So there is signal there, even though you can't see it in the phase values themselves. They vary systematically between two images, even though the individual values are completely random. So this phase is just a raw interferogram. This actually contains a lot of different things. So we'll talk about all those different components. So we have Earth curvature, which is basically what sort of what Catherine was showing with the look angle being off to the side. There's going to be a difference in the distance to the satellite if the satellite didn't exactly precisely repeat its orbit. And we'll get the same thing with the topographic phase. So the topography will be viewed from a very slightly different angle, and that'll contribute to phase. Then, of course, we have deformation, but we can also have a little bit of error in the orbits. There can be issues related to the ionosphere or the troposphere. There's even actually some difference from the tides, so that you know about the tides in the ocean, but the solid Earth also has tides that cause it to move up and down by several centimeters. And so that actually can contribute to the phase. And then there's noise, which is a kind of just a sort of random process in the pixels themselves. So if we think about what we have and what we want, we actually know the Earth curvature and the topography pretty well these days. That wasn't always the case, but nowadays it's pretty good. We're looking for the surface deformation, right? That's typically what we want. We know the tides. There's models that can correct for that. We don't know the troposphere delay, and we don't know the phase noise. And then the orbit and the ionosphere are kind of variable. So in some cases we can correct for that, but not always. So we'll talk about each of those components. So the first one, Earth curvature and topography, you might think that isn't really a large effect, but actually it depends on that distance between the satellite's initial position and then when it repeated the orbit. It should repeat its orbit exactly, but there's things like atmospheric drag, even at 700 kilometers altitude. And that atmospheric drag can vary depending on things like the solar activity that can heat the Earth's atmosphere and cause it to expand. And so you actually get variable drag on the satellite that makes its orbit a little bit unpredictable at the range of maybe tens to hundreds of meters. So sometimes the satellite won't be exactly in the same place. And so that can contribute to this effect. So this is what this is an ERS image from the 1990s. And this is actually in Southern California. So one fringe represents 2 pi phase change. So you can see the sort of the black to white fringes. And then they're repeating many, many, many times across this image, right? And so it turns out that that is mostly due to Earth curvature. And then there's some extra weird kind of patterns in here that you might be able to see, and that's going to be the topographic effect. So we can calculate how the phase would be different. So if we have our 2 reference and repeat orbit positions, they're going to have a slightly different range. And we could think of them as nearly parallel lines because the satellite, remember, is 700 kilometers altitude. So it's looking at very, very close to parallel rays to the same pixel. And so we call this the parallel component of the baseline and the perpendicular component of the baseline. And the total sort of difference, vector difference between the 2 orbits at a given location in the orbit is called the baseline. And so this is just going to be sine of the difference between these 2 angles. This will be like the incidence angle, and this will be the angle between those 2 orbits. And then this would be the perpendicular baseline. So I'm not going to go through the derivation of this, but if you look at the phase due to the curved Earth, it's related to the range, the height, the wavelength, this baseline times cosine of theta minus alpha. And then the phase due to topography is going to be a similar thing with this baseline times cosine of theta minus alpha. So it turns out that perpendicular baseline is the component that actually matters in terms of producing this Earth curvature and topography effect. The parallel baseline would change the phase, right? But it'll be constant value because it's just pretty parallel across the whole phase, across the whole image. So it's going to not contribute that much. So we can pretty much ignore that component. So you'll often see images like this when you read the InSAR literature. So people like to plot time of the image acquisition versus perpendicular baseline. So you'll see all sorts of interferogram networks kind of shown like this. So this is just one example. And so this perpendicular baseline gives us information that tells us about how much that topography might be contributing. So if your baseline is too large, the topography could contribute a larger amount. We don't precisely know the topography in all cases, and so there could be a little bit of extra noise. There's also a critical baseline that I'll talk about later, so you can't go beyond a certain value or you'll lose coherence. So from that image that we had before, this one, if we remove the Earth curvature, then we end up seeing something like this. And so now you can see the topography. And so the phase changes. This is actually like a topographic map with contours, essentially. And so this can actually be used to measure topography. So if we think about the phase change across the image due to that curvature or the topography, if the baseline is so large that the phase change per pixel is greater than like one wavelength of the satellite, then it'll be aliased, and so we won't be able to recover that. So we can actually calculate what that turns out to be. For ERS and NVSAT, the range was from about 1 to 3 kilometers. So at the near range, 1 kilometer, that formed kind of the limit. So you can't form an ERS interferogram that's going to be coherent with a baseline longer than about 1 kilometer. And the coherence kind of decreases gradually as you get up to that point. So you don't want to make images with too large of a baseline. For ALOS, it was a lot larger, 3 to 9 kilometers and 7 to 18, depending on the bandwidth, depending on the mode. So these would be different resolutions, if you remember what Catherine talked about with the range resolution. So if we look at the Sentinel-1 value, so we have a 5.5 centimeter wavelength. The range might be something like 800 kilometers. The range resolution might be around 5 meters. The incidence angle, 30 degrees. So these are all just kind of approximate values. We could calculate the critical baseline for Sentinel, and it's about 5 kilometers. So this is actually much better than ERS and NVSAT. The main difference is this range resolution is much higher, right? So they had about similar wavelength range and incidence angle, but Sentinel-1 has a much higher range resolution. And so its critical baseline ends up being a little bit larger. So it's not something that we have to worry as much about with modern satellites typically, because they've gotten to be higher resolution. And so the critical baseline is kind of further away. But okay, so if we think about what we want to do, we could form a bunch of interferograms like this, where we form sort of short time spans. So we're not looking for deformation, but we have large critical baseline. And so, we're not trying to get more than the critical, or not more than the critical baseline, but large perpendicular baseline, right? So here in meters, hundreds of meters from minus 600 to plus 600. So we couldn't form these longest ones, but we can form a series of these, make these little chains. And from that, we could then average all of those images together. We call that stacking, and form a topographic map, right? So this is a topographic map of that area that was shown in the example image. This is the Salton Sea. Palm Springs is kind of over here. And so this was actually how topographic maps were made in the 1990s. So you didn't have a high enough resolution topographic map to remove it from your interferogram, so you had to make your own. So you had to do all this extra steps of processing like this and average those interferograms all together, make your estimated topography, and then subtract that from the rest of your interferograms to measure the deformation. So it used to take a lot longer to do this kind of work, right? Here's an interesting idea. What if we had a 0 time span interferogram? So one of the big problems with doing this kind of work is that we always have atmospheric noise. And so the atmospheric noise is contributing error to our topography. And so it makes it, that's the main limitation on the resolution and accuracy of those topographic maps, is that they can have atmospheric noise. So if we had a 0 time span interferogram, somehow we have like the images both being collected at the same time, still with a perpendicular baseline, then we wouldn't have any atmospheric noise because it would all just cancel out between the two images that were collected at exactly the same time. So that's kind of sounds like maybe a crazy idea. How would you fly like 2 SAR satellites at the same place with a tiny offset between them? But actually this was done. This was done in 1999 and 2000 by the SRTM mission. So SRTM stands for Shuttle Radar Topography Mission. And so what the space shuttle did was fly upside down, pointing at the Earth. It had an antenna in the bay, and it had an antenna out here on this long boom that I think was maybe about 80 meters to provide a perpendicular baseline. And so it was able to do that so it could actually collect 2 images at the same time. So the one in the bay would transmit, and then both of them could receive. And that actually gave them the ability to do a 0 time span interferogram. So SRTM is still one of the sort of standard topographic data sets that we use, even though now it's like 25 years old. So prior to this, the best global data set available was about 1 kilometer resolution, and SRTM is now the standard about 30-meter resolution. You can see it's much, much better. And nowadays there's even other missions that are doing this. So TandemX, you might have heard of, is 2 satellites that fly in formation, and they're an X-band satellite. So X-band is a shorter radar wavelength. We'll talk a little bit about the difference between those, but there's another mission plan for Tandem L that I've had to update the date for. So the last I checked, I did check this again, and it says still 2028, but you know how these missions are. They tend to delay a little bit. There's always more complexity involved in building something as complicated as a satellite. So what do you think about this image? This is an interesting one that I found on Twitter. You can see this a few years ago now, but somebody posted, found some weak uplift signals. However, I detected a strong uplift signal at Mount Ararat in Turkey. So Mount Ararat is this mountain here, and it's believed to be an extinct volcano. So it's kind of surprising if it could be deforming, right? That would certainly be concerning. So you can see that there sort of highlighted. And they posted a couple of images, right? So here's a second image showing the same thing. So what do you think about this image? Just think about it for a minute. Try to notice anything odd about it. So one thing that stood out to me is this sort of line when you look at the phase, right? You see this sort of very sharp horizontal and vertical line in the image. And this image has been geocoded, so these lines are facing exactly north, south, and east, west, right? And so when you download SRTM from the USGS website or NASA or wherever you download it, it usually comes in 1 degree tiles. It comes by 1 degree tiles, and you have to download all those tiles and then combine them together to make your DEM. So it seems like the replies from David and Eric Fielding said, it looks like you might be missing a DEM tile, right? And so, in fact, I'm pretty sure that's what's the case. So this person's DEM correction, unfortunately, didn't succeed properly. And this is what your image would look like. So this is actually a measurement of the topography. And the reason those two images are slightly different between this one and that one is they probably have a different perpendicular baseline. So they end up with a slightly different phase, but you can see that they're very kind of similar to each other and they're both basically proportional to the topography. So something to watch out for. Another thing to watch out for is the reference elevation of your DEM. So typically, when we measure elevations, we want to think of them as relative to sea level, right? It makes sense that when you're at the beach, you should be at 0 meters elevation. And so most DEMs that you download are relative to sea level. So sea level follows what we call the geoid. So the geoid is sort of an equipotential surface that the sea sits at. And the standard geoid that was used for SRTM is EGM 96. It kind of looks like this map. It's sort of very slowly varying across the Earth. But when we're doing our InSAR processing, it's much more convenient for processing the orbit data if we use them relative to the ellipsoid, which is typically we use WGS 84. And so there's a slight difference between those. So you need to make sure that you remove the geoid from your elevation data set before you process it. If you just take raw SRTM elevations or some other DEM elevation, you might have this geoid error in your data set. So make sure that you remove the geoid height. So the DEM Gen website for GMTSAR, there's other methods also available online that will do that for you and give you a WGS 84 relative elevation. So, okay, so now we've removed our elevation. We can finally start looking at deformation. So here's a great one. So this is an old image from that same area in Southern California. This is the San Andreas Fault, and it's showing a little bit of creep, a little bit of offset along the fault line. And this was something that I studied during my PhD in San Diego, and several other of the instructors I think have also worked on this. So it's a pretty neat signal. And then out here, just off the edge of the image, are the Landers and Hector Mine earthquakes. So this image, if you look at that time span, those lines indicate the times of the earthquake. So this is a really long time span interferogram, almost 10 years. I think this is number of days. So it's like 3,000 days interferogram. And so it includes both of those earthquakes as well as that fault creep. And the image is still like relatively clear. We don't have a lot of noise in the image, which is pretty impressive for a 10-year interferogram. That's not always the case. So here's an image from the Wenchuan earthquake. This was collected with the ALOS-1 satellite by Xiaopeng Tong and or processed by Xiaopeng Tong. So you can see the fringes here related to the earthquake very clearly, but over here on this side, they are really noisy and it's very difficult. You can kind of see that there probably should be some fringes in there, but in close to the earthquake rupture area, you just can't really make anything out. So that's kind of difficult. Here's another case recently. So this is an interferogram from the Mandalay earthquake in Myanmar that just happened in March. And so you can see the fringes pretty clearly in some parts, but near the fault and also in these other areas, you just get a lot of noise, right? You see all this kind of crazy fuzzy scatter. So we call that decorrelation. So decorrelation happens when the phase values get randomized between the two image collection times. If you think about what's happening in a pixel, one pixel contains actually a lot of different reflectors within it, right? If the pixel size is 10 meters, but the radar wavelength is 5 centimeters, the radar is reflecting off of everything within that pixel and bouncing back toward the satellite. So you might have a case where your pixel just has a lot of random reflectors in it, or you might have a case if there's like a building in it or something else that brightly reflects toward the satellite, you might have one reflector that dominates, and then your phase might be more stable. So what typically happens is in some areas, you just get this sort of randomization process of the ground surface just changing over time, and we call that decorrelation. So we typically try to apply some sort of filtering process to fight that decorrelation. So, this might be what the image looks like before filtering, and then after filtering, it gets cleaned up a lot. So a common filter that we use is called the Goldstein filter, but there's other filter options as well. So there will be more discussion about that. You'll get to actually, when you process your own data, take a look at the phase and phase filter, and you can see the difference between those two. So here's a case. This is an interesting one from Mount Agung, which is in Bali in Indonesia. And you can see that this is after filtering. There's still a lot of noise over here. This is because there's basically vegetation. It's a dense kind of almost a jungle on this side of the mountain. And so there's just nothing that you can really do to process that noise to make it go away. But on the volcano itself, we see this pretty clear circular signal. So you might think, okay, is it topography? No, in this case, we carefully corrected the topography. But is it deformation? So this interferogram was formed at a time when Bali was undergoing a seismic crisis beneath Mount Agung. And so there was a lot of concern. The last time Mount Agung erupted was in the 1960s. It caused a lahar flow that killed a lot of people, and it's really kind of a scary volcano. So people were really concerned about this, and they looked at this interferogram and said, what should we do? So what do you think? Well, it turns out by forming the next interferogram in the time series, we saw that apparent deformation went back the other way. So it was actually probably atmospheric noise. So even so, the volcano did erupt. So there was certainly a magma intrusion, and the volcano did erupt. But the later analysis showed the magma intrusion was not nearly as big as that initial interferogram indicated. So this is one of the tricky things. So when we're looking at interferometric data, one of the big problems is troposphere delays. Typically we call this atmospheric noise. And you can have things that look like this. So this can look almost like topography. So this is a DEM of this island, El Hierro. And I think this is in the Canary Islands. So this is an island, it's not deforming. There's no signal here. There's no deformation in these images, but this one looks like topography. And this one just looks like crazy random noise, right? You just see all these crazy patterns. And so typically we see this type of thing in all of our InSAR images. And so it's one reason why we have to take many images over time and average them together or form a time series. There are approaches to try to remove the atmospheric noise. And so we'll hear lots more about that, I think, tomorrow. There's several talks about ways and approaches for removing atmospheric noise, but none of them are perfect. So we always end up with a little bit of atmospheric noise in no matter what we do. Another thing that you sometimes see is an image like this. And this was one from the Gorkha earthquake in Nepal in 2015. And you can see the earthquake signal here. So the signal is there, but there's this crazy amount of fringes across the image. Initially, we thought this might be an orbit error. So maybe we misprocessed the satellite position or something, but that seemed kind of implausible. It turns out this was an ionosphere effect, and we just had never seen this large of an ionosphere effect before because the ALOS 2 images are so large. They're 5 times larger in both dimensions than the old ALOS 1 satellite images. So we were used to looking like a small sort of postage stamp size areas and seeing 4 or 5 fringes, but this one has something like 30 fringes across the frame. So it's just a huge amount of ionospheric noise. So oftentimes ionospheric noise looks like this. Sometimes it looks like these kind of streaks, these very like sharp variations. So the ionosphere is an interesting part of the Earth's atmosphere that is electrically charged. And so it has a kind of a different way that it interacts with the radar signal. So it actually has a different index of refraction depending on the wavelength. And so because there's different index of refraction at different wavelengths, we can use something called a split spectrum approach that allows us to correct it. So we exploit some of the bandwidth of the image that's actually sampling at slightly different frequencies to slightly different wavelengths, and that gives us enough difference between the wavelengths that we can actually measure the ionosphere and try to remove it. It tends to increase the noise of the image because we're using up some of that information that normally would be used to form the high resolution information. And so it can fail in some cases. But here's a case from my PhD student, Cheng Han, who did a great job correcting ionosphere data in Bangladesh, which was a very, very challenging area. So it's very wet. There's a lot of vegetation. There's a lot of farming. There's also a lot of ionospheric noise because it's right on the magnetic equator. And so that tends to be where you get the largest ionospheric signals. So I think I'm a little over time. The last thing I wanted to talk about is just the different wavelengths of different satellites. So X band is about 3 centimeters, C band is about 6 centimeters, 5 to 6, and L band is sort of 20 to 24 centimeters. And so they're going to reflect off of different parts of the vegetation. So if you think about X band, 3 centimeters, it tends to reflect off of like the leaves and the tops of small vegetation. C band might reflect off of like larger branches, or it might also reflect off of leaves. L band tends to reflect off of things like tree trunks. So it's going to be much more stable in terms of the phase values that we recover. So here's a comparison from the island of Hawaii. And so this was comparing a C band and an L band image. And so you can see this contains the topography information, right? This is from the 90s. But the C band has many more fringes, right? So there's higher frequency, so it's got much more fringes. The L band has lower fringes, and you can see a much better coherence, so less of that decorrelation related to vegetation. So this part of the island of Hawaii is very, very vegetated. It's basically a jungle, and so in that area, L band works much better than C band. But on the other hand, the ionospheric delay is related to the square of the frequency, and so, or the square of the wavelength, and so it's 16 times worse at L band because it's about 4 times longer wavelength. So you have trade-offs, right? But we typically tend to like longer wavelengths for doing InSAR. So here's an example for the X band image of the I think this is the L'Aquila earthquake. You can see that there is an earthquake in there. There's some fringes, but you don't really recover the signal well enough to model it, right? So the fault is over here. L'Aquila is here. It's mostly decorrelated, and this is because Italy is vegetated. In C band, we do a lot better. So the C band recovers the image pretty well in all the areas that are basically grasslands, but in the areas that are forests, we can't recover that. And so you see sort of areas that are grassland, we can recover the phase. This is pretty good. You could use this for modeling. You're missing a little bit of the data out here, but overall, pretty good. The L band, this image looks kind of funny, but it has very few fringes, right? Because the wavelength is longer, so the deformation per fringe is much more. But the coherence is basically perfect. There's only a few little areas that might be related to layover or shadowing of the image in the topography. So basically the L band works through vegetated areas, right? So NISAR is going to be an L band satellite as well as an S band. S is in between L and C. So NISAR should have really good coherence. ALOS 2 is also good coherence from the L band. But it's susceptible to the ionospheric effect, so you have to take that extra step for the correction. So thinking about sort of conclusions, watch out for your perpendicular baseline, especially if you're dealing with older satellite data. That's something that you need to be aware of. If you're dealing with Sentinel or modern data, most of the satellite operators these days control the baselines better. So they have kind of like a more real-time operation of the satellite and keep it within a small perpendicular baseline. But that's not always the case. It's something to watch out for. You do need precise orbit information to have good phase, but that's pretty typical these days. We'll talk about how to get those orbit files and everything. Densely vegetated areas, if you want to work in an area that's got forests, you probably need to use L-band data. You can sometimes get by with Sentinel because it's got a short acquisition time between images, so it sometimes works okay, but it's going to be a lot more challenging with shorter wavelength data. And X-band interferometry, basically you should work on rocks. Rocks and cities, that's the best place for those. But atmospheric effects are typically our biggest issue that we deal with, so we're always thinking of ways to try to remove those. So whether using a weather model or different careful averaging or kind of correction methods. So, okay, thanks a lot, you guys.
Thanks, Eric. Actually, I think we're almost exactly on time. And I see lots of questions in the chat, so in the Q&A, so keep those coming. And then there's a Discord site where we could also ask questions and people could answer. So I'm sure there's lots of questions.
That's right. I forgot to mention some people were saying they had a little trouble with the Discord. So it looks like about 40 people have been able to join so far, last I checked, but give that a try. If you end up getting some kind of error, maybe we can troubleshoot it tomorrow. The thing that I did, it works fine for me. I installed the app on my computer rather than trying to access it through the web. But I'm not sure what's going to work out best in your case. So if we need to generate a new link or whatever, just let me know.
Great. So the last discussion today is by Anne, and she's going to talk about SAR acquisition modes. How can we make that SAR swath wider so we can repeat more often?
Yeah, and please keep the Q&A coming. So one student asked where you can get all the slides. And right now, they're later going to be publicly available, but currently I already uploaded the all day one lecture on Moodle. So you should have already received an account for logging to Moodle, and that's where all the slides are placed. And later you're going to use that website to upload your final presentation and if you sign up for the breakout session. All right, let me get started. So this is the last presentation for today about SAR modes, imaging mode. So it is actually a strong connection between this lecture with the previous lecture Catherine mentioned about SAR series. So the idea is here we would like to link all these different SAR imaging geometry to recent SAR missions. And no matter what imaging mode you use, and you should get a pretty good quality interferogram for surface deformation analysis. But here the trade-off is really about spatial resolution and a signal noise ratio. And more importantly, we hope to get a wider swath so that we can reduce the satellite repeat cycle. So that turned out to be a very critical trade we would like a imaging SAR mission to have. So I'm going to start by revisiting the SAR imaging geometry that is currently used for the Stripmap mode. So for the earlier SAR mission, like the ALOS TOPSAR and the ERS satellite, so a very common data format you will see is what it called the Stripmap mode. And so we're going to start with that, and then later talk about limitation, and then introduce some of the more modern imaging mode. So for the Stripmap mode, the radar satellite can be on board of an airborne sensor or a satellite or a space shuttle. So there are two important directions that the radar defines. So for SAR image, it is a 2D image in 2D mapping. So the first direction is along the flight direction. So this is what we call the azimuth direction. So the second direction is that when the radar periodically send out the pulses, it looks sideways. And so it will illuminate the ground that is kind of illustrated here. So from the near range to far range, so those pixels have a different distance between the radar to the ground pixel. So that's the range direction. So another way to talk about the azimuth direction is the along track direction, that is along where the satellite is moving, and the range direction is the cross track direction, is towards the side where we are looking. So you can imagine at a given time, the radar satellite send out a pulse that illuminated ground. So that is, you can actually calculate what's the, if you're shining a flashlight on the side, you will be able to illuminate a part of the ground, right? So based on the antenna theory, you could actually calculate what the radar print looks like. And you can imagine that for this radar footprint, you can divide them into many, many bins. Each of them share the equal range. So at a given time, the target that is closer to the satellite will return back a little earlier, and the target at the far range will return at another later time. So this is what we call a line of radar image. So that's all collected at a given radar location. So the Stripmap mode, the radar antenna will point into a fixed direction, and then the next time it will move forward to a little bit forward and make another acquisition that illuminate a slightly different path of the ground forward. So as we keep sending additional pulses, then you start to have a scan of the ground image. And in order to better understand this two-dimensional mapping, so let's first take a look at the imaging geometry in the range direction. So here, this particular dot, if you could see my mouse, is a satellite, is flying into the page, and this is a cross range direction. So here Z is the topographic height of the radar satellite above the ground. So typically for spaceborne imaging, Z is around 700 kilometers. So it's pretty far away from the target. And here there is a very important angle that is called a theta. So this is what we call the look angle. So it means if you're looking sideways, and so the angle between the vertical direction and the way you're looking. So usually for imaging radar satellite, you can think about theta is typically about 24 degree to about 30 degree-ish. So that is the kind of range we typically do. We don't really put the theta to be 0, because if that's the way you're directly looking down, and that is what we call a radar altimeter. So instead of having illuminated swath, if your theta is 0, then you only illuminate a spot, then you get a transect instead of a 2D radar image. And we know the antenna pattern, so we can, based on this imaging geometry, as well as the width of the antenna, if you're assuming a rectangular antenna, to calculate the swath on the surface. So we have a simplified equation here. So you can see Z is known, theta is known, and the this angle from is a lambda, that's the radar wavelength, how wide this swath gonna be. It's really with the lambda divided by W, where lambda is the radar wavelength, and W is the physical width of the antenna. So you can actually calculate, we did a calculation about how wide the width is, and that's actually the center of this lecture is with different imaging mode. You're hoping to be able to have a wide width during a pass. And the reason is because if you can illuminating a large portion of the area, it takes less repeat to imaging the entire Earth, then you can consequently come back to the same area of interest, take another measurement over a shorter period of time. So that's why in the early mission, you get a revisit cycle of every 35 to 46 days. But now for the Sentinel, you can get a revisit cycle of every 12 days. That is largely due to the ability to be able to imaging a wider swath for a given flight path. And in the range processing, because of this, we need to not only ideally like to have a wider swath, but also a good resolution. So in terms of resolution, because this azimuth and the range direction is processed differently, and that's why the resolution for the range and azimuth direction is also differently. So in the range processing, as Catherine mentioned, we're usually transmit a wave that is called a chirp. And you can think with the received signal, of course, there are some added noise here, but the raw received signal from the near range to the far range may look like that. This corresponding maybe 3 target that is located at a slightly different range location. And so it's just a duplicate of the signal we sent. And in some cases, if you have a brighter signal, then the amplitude of that particular target is going to be bigger. And if you have a darker sample, then the return of that sample is going to be darker and so lower amplitude. So you can see without additional processing, the range resolution would be related with the pulse length here. So you could not identify two targets that is so close so that these two return echoes start to mix it together, right? So that's why without additional processing, and so the resolution is actually related with how long this wave you're sending out. Luckily, typically we're gonna have a matched filter process, which means you know what signal you're transmitting, then you're just slide the signal over with to cross multiply with your received signal. So you could imagine when the transmitted signal, that's what we call the template, matched to one of the received echo, you get a big spike here. And then when you slide it to the second pulse, then you get another spike. So that's the process. The third line is what the range compressed signal looks like. So there are two benefits from this process. The very first one is after the cross multiplication, the spike gonna be a lot higher than without the compression because you're actually cross multiply the of each of the sample and sum them together. So it's gonna have a much larger spike. And also you can see for the first target that compressed signal is much compressed in time, and which means now you are able to distinguish two targets that is more closer to each other, right? So that's why this matched filter process not only improves the signal to noise ratio, but also improves the range resolution. Here, you can think about the horizontal axis is the receiving time, and so because the radar travels in the speed of light and with two-way travel. So with this time information, you could convert that to the range of the target. So that's our first coordinates. And so in the azimuth direction, that is a slightly different picture. So as we mentioned, the radar is moving, and so at a position 1, it emit a pulse. And then once it moves to the next position, if they do the same thing, emit another pulse, collect near to range, and we can just stack all those lines to get an image. So this particular measurement without additional processing is called the real aperture radar, because you know, like a SAR stands for synthetic aperture radar. So there's another real aperture radar. So this is the basic geometry for real aperture radar. So in this real aperture radar, it becomes clear your resolution in the azimuth direction is really with how wide this radar footprint is in the azimuth direction, because you're taking sequential samples like over non-stacked footprint, and so the resolution would be really with this length. And again, based on the imaging geometry, and we can actually know the length of this particular radar footprint on the ground is really with the R, that is the range of that target, times radar lambda divided by L, where L is the length of the radar antenna. So people did we can do a straightforward calculation, plugging some numbers for typical airborne system and a spaceborne system. And the reason we actually switched to the synthetic aperture radar is because you can look at those resolution. And so it's probably you can use a real aperture system when you are talking about the airborne X-band system. Even that 450 meter azimuth resolution is not that great, but definitely once you're in the spaceborne platform, the real aperture radar is just not a feasible option. So the way to deal with the synthetic aperture radar is that if we go back in time, and you can see this radar footprint is large, and the satellite is flying at some kind of a known velocity. So you're sending out a pulse, and then you fly it, and so there's a very long wait period and until you fly to the next position and send another pulse collecting that covers a new area. So instead of doing that, you could actually sending out many more pulses as the radar satellite flying over to have those radar footprint like slightly move forward each time, but with a very small increment. And in this way, a given particular target will be illuminated at many pulses because of the radar footprint is so large. So when the radar is right here, it actually covers it. But when the radar platform moved forward, that target is still within that radar footprint. So you could have many lines of data that contain the same target. And through some post-processing analysis, and we know we could combine this data since we know the satellite motion and equivalent as a longer synthetic aperture. And if you go back to the previous one, when you have a longer synthetic aperture length, your azimuth resolution goes down, and so resolution smaller is better, right? And so, and to the end, it's very surprising after you go into all the geometry, the azimuth resolution for the synthetic aperture is a very simple expression that is L divided by 2. So this means the SAR algorithm can achieve a very high resolution even for a spaceborne satellite, right? And so means if you have a length of the antenna, the resolution is L divided by 2. But of course, there are other constraints that make it impossible to make an infinite small like a antenna length. So, but in terms of resolution, and we kind of solved this problem. So that's kind of the typical idea about the Stripmap processing. The radar holds the antenna that is pointing to a particular direction. It sends out the pulses and receive echo from near range to far range. And as it moves forward, it's keep sending out the pulses at a fixed small time interval. That's what we call the PRF, or pulse repetition rate. And then by combining this data, we can do the range processing, compress the data in the range direction to achieve high resolution, and also in the azimuth direction through synthetic aperture algorithm, and to get a very high resolution in the azimuth direction. And so another thing that comes out in the imaging mode when you have the radar data is a lot of the mission will deliver data with a different polarization. And so this is typical, just means instead of getting one SAR radar image, and when they are operating at a pulsar mode, you can get sometimes 2 images or 4 images, depending on the polarization of the EM wave you have for transmitting and receiving. And why do we need this different polarization? The main use for pulsar data is that if you can imagine, if you have one particular target you're interested in imaging, and so they should look the same, have similar, like if 2 targets are identical, no matter what polarization, they should give you some kind of a similar property, right? And but it's not but for 2 targets that are different, sometimes they might look the same in one particular channel, but not the same on the other one. So when you are able to have maybe multiple polarization, you can actually form a false colored image that allows you to be able to kind of do better classification of what is on the ground. And so here is another illustration about for the Stripmap mode. The reason it is usually used for the earlier SAR mission is because there is actually a limitation on how wide the imaging swaths we can achieve. So this is essentially come to the 2 requirements when we are designing an imaging radar system. The very first thing is about how long we have to wait until we can send out another pulse, right? And so ideally, when we are at a position, we would like to send out a pulse, collect data from the near range direction to the far range direction. And then after the far range signal was received at a later time, and then hopefully you're sending out a pulse for a new line of data. And you don't want to send out a pulse before the far range pixels return hasn't been received yet. So that create a bound of the how long we have to wait before we can send out another pulse. So that's the maximum PRF, because PRF is a frequency. You have to wait for a little longer. And so that's a maximum PRF, the upper bound. So there's also a minimum PRF, because when you're trying to sample the azimuth spectrum that covers the ground, so they have a different Doppler frequency, because they are like, for some of them are forward looking, some are backward looking with respect to radar. In order to sample the full spectrum in the radar processing, you have to sample at a fast enough rate in order to capture all the response. Just like if you have a signal, you cannot sample too slow, otherwise you might lose information. But these two are kind of, you have a separate requirement. So basically your minimum PRF cannot be larger than the maximum PRF. Otherwise, it doesn't work, right? And so with all this trade-off with Stripmap mode, typically you cannot have a swath width, that's from the distance between the near range to far range, over 80 kilometers. So that's the limitation. And you can know for Sentinel, each of the imaging frame, the width is about 250 kilometers. And that's why, and also the ScanSAR. So that's why they're actually moving away from the traditional Stripmap mode. And so we're gonna introducing these 3 different imaging mode that trying to deal with this limitation. So the very first approach to get wide swaths is using ScanSAR. So this is used in ALOS PulsAR and ALOS 2. And so you can kind of get a comparison of this image on the right. For the typical Stripmap mode, the width is typically about, I think 60 kilometer-ish, that if I recall right. And then the larger square shows the ScanSAR mode, and that over the same area. So you can see that's roughly 5 times larger in terms of the width. And usually this is desired because sometimes when you have a really large earthquake, it spans a very big area. And so the deformation pattern, so if you have those smaller Stripmap mode, you will have to stitch them in the post-processing, which can be very tricky for calibration purpose. And so the way ALOS be able to like achieve the ScanSAR mode, we kind of having a imaging geometry illustrated here. So here you can see this Stripmap mode about 70 kilometers. So this is like illustrated in this dark gray area. So so the satellite is going like visit one synthetic aperture length. That means like a distance and acquiring data for a particular target. So for the Stripmap mode, the look angle stays the same. So that's why it covers the same subswath, right? And so all the other possible imaging mode is just unutilized. And in this way, we get our Stripmap image over this narrow area. And for the ScanSAR mode, is fully utilized all these 5 possible subswaths. So instead, it divided all these pulses. So because we have a lot of these redundant pulses as the radar travel along the track direction. So instead of using all the pulses over one subswath, we use 20% of the pulses. And so that's for imaging this swath. Then they can steer the radar antenna and change the look angle so that it then can use another 20% of the pulses to sample the swath number 2, 3, 4, 5, and then repeat this whole process. And of course, this process has a trade-off, is that for the Stripmap mode, we use all the pulses that to form the image. So you can think of the synthetic aperture length is the entire synthetic aperture length. But when you are dividing all those pulses into 5 separate chunk, equivalently, the synthetic aperture length is dropped by 1/5. And the sacrifice is that will lead to reduced azimuth resolution. As we mentioned earlier, there's a simple relationship with how the azimuth resolution is affected by the synthetic aperture length. But luckily, typically radar has like a meter level resolution. It's not a big deal. So most of the applications, they would be happy with 100 meter of resolution. So that actually makes it's actually okay in a lot of the case to trade off between a slightly worse azimuth resolution versus a bigger coverage over a single pass. And here are some additional limitations. So in this, there's another foundational assumption that InSAR technology require is that as you, what InSAR really compute is when you have a multiple SAR images, you are calculating the phase difference between the two SAR acquisition. So, so there is a requirement that image of the radar satellite in a frozen imaging orbit. So that's why if it flies over in a ScanSAR mode, the pixel was covered by subswath 1, and hopefully the next ScanSAR coverage, that whole pixel is still covered by the subswath 2. If there is a mismatch between the subswaths, then the look angle change, and then you start to lose like the phase coherence. And so here's an example of an ALO ScanSAR image. So you can see at the top, the phase looks more consistent, coherent. As it goes down, more of the decorrelation occurs, mostly because of this burst alignment is starting to degrade. And so for ALOS 2, because of the better orbital control, so I think this problem is getting reduced, this issue. But again, still the ScanSAR to ScanSAR processing and require all this, there's some complication with that. And also you can see this amplitude image, sometimes they are less consistent across this burst. So, and that's why for Sentinel-1, they're kind of trying, the goal is to trying to mitigate those limitations from the ScanSAR imaging mode and to be able to allow more uniform amplitude across the swaths. So again, instead, they still divided all the bursts into 3 subswaths, right? And so this is TB1, TB2, and the TB3. So they have 3 subswaths that have some overlapping between them that facilitate some of the calibration. And also, beyond just steering the satellite imaging geometry in the look angle, so you can cover different subswaths. Also there is a steering from the backward to forward, so so that it can first start, instead of holding like in the Stripmap mode, like pointing to a particular direction, the antenna is actually steering from backward to forward. That will allow so the satellite during the subswaths cover a bigger area, and the steering is designed so we will acquire image from subswath 1 to 2, 1 to 2 to 3, and then you go back to subswath. There's a seamless stitching between them. So that's kind of the overall idea. So of course, this kind of design allows a wide swath, but it comes up with some issues. So one of the issues is that the antenna is constantly steering at a pretty fast rate, right? And so that usually means if you're looking at a spectrogram of the data, so the horizontal axis is burst times, and then the vertical axis is normalized frequency, you can see a larger Doppler rate variation across the spectrogram. And so typically for traditional radar processing, we would like to have the data at a near 0 Doppler rate. So, but that's usually okay because for Sentinel, they know how fast the antenna is steering. So we could actually correct this issue and by a process called deramping, and so that the data is as if we are collected at 0 processing, and this allows you to be able to perform some like a radar processing, like a resampling those processes using the old way we process the data, and after that we can re-ramping back the signal. So that's issue number 1. So most of the radar processor, including GMTSAR, already automatically handle this for you. There's a formulation in the Sentinel documentation of how to do it, and the user usually don't have to worry about that. And the second problem is through this new TOPS imaging geometry. Here you can kind of see the subswaths 1, 2, 3, and after this was collected, you can see this one moved a little forward because the radar is moving, and this one is here, and then it start to seamlessly doing the going back to this one burst at a time. So for this processing, because a burst and a substantial burst, so one of them is forward-looking, one of them is backward-looking, so they have a very different like Doppler rate. And so that usually means it's very sensitive to if you have a small misalignment in the azimuth pixel location, in the azimuth direction. So traditionally for Stripmap mode, we usually require the pixel misregistration to be about 0.1 pixel. So each pixel is typically a couple meters, right? And so that's the tolerance we can do. But for the TOPS mode, and there is a relationship between the amount of azimuth misregistration will lead to the additional amount of phase difference. And so typically, if you want a seamless connection with a smooth phase, you would need about 0.01 pixel accuracy. That's translate to about 5 centimeter accuracy in terms of how well we know the pixel location is. So here is an image. So on the left is our SAR radar data, and on the right, the SAR amplitude image, and on the right is this Sentinel data. And you can see this is a when you have a larger, even like I would say 0.1 pixel is not that large, but you can definitely see them in the image. So you see this phase offset along the burst. So this is one particular subswath over multiple bursts. And so within each sub burst, then the phase actually is correct, but there are some constant shift between them. And this just makes the processing very difficult. And so luckily, in most of the SAR processor, we abandoned the old cross correlation approach to do the image alignment. So we know where they are on the ground. And so that's based on those feature tracking and cross correlation. But for the Sentinel processing, in part thanks to the precise orbital determination. And right now it makes more sense to just directly use the orbital information and the terrain DEM to figure out where each measurement is on the ground. And that actually allows us to get about 5 centimeters that required accuracy, just entirely rely on the orbital information that David mentioned, to align the image and get rid of those artifacts. I'll give you an example, but in most of the cases, using the orbital information alone should be able to get rid of the noise. So you can see on the left is one with a slightly, you can start to see some line artifact. That's a phase, small phase discontinuity across different bursts. And after you align them, there's no this kind of line artifacts. In most of the time, rely on the orbital information itself is sufficient to correct those artifacts. But sometimes the presence of a large ionospheric artifacts when the solar activity is high can lead to additional misshift that you couldn't correct based on the orbital information alone. So that's why even with all the precise orbit, sometimes you might still see some SAR image that has some of these artifacts that has a phase discontinuity across a burst. Xiaohua showed an example earlier that from the ionospheric noise that can be further corrected with additional enhancement. And so finally, but not last, so last but not least important, so we are also talking about the upcoming InSAR. So they're trying to design a different imaging mode that's called a sweep SAR. And so the limitation for Sentinel and ScanSAR is trying to subdivide the ground into 3 subswaths and then utilize fewer bursts and equivalently as reduce the synthetic aperture length and to get a wider swath. But the sweeps are trying to attempt to have a more uniform illumination across the entire swath to achieve the full resolution. So the sketch here is kind of give you an idea how it works, but the actual implementation, they don't really just steer the antenna this way. So the idea here is that when you're trying to illuminate the swaths, and you could try to have a smaller antenna width, and that will lead to a larger angle here, and that's why you can illuminate a larger footprint across a track, right? And so that's a big area. But the limitation for that is you have to make sure to wait to send another pulse until the return from the furthest point to come back. Right, but you could actually eliminate that constraint by sending out pulse like illuminate the entire area, then like trying to narrowly focus on a smaller subsource at a time for the receiving. So they have 3 different receiving area narrowly focused on a smaller area and stack them independently, process them. So in this way, you could send out the pulses at a shorter interval than the last pulse to return. And so that's kind of the idea to work along that limitation we mentioned earlier. And so here there is a sketch I showed from the JPL website. There are more information about that. Each red is when they're sending out the pulses, and each of the 3 sub-beam is trying to process data received from a portion of the ground. And so last, and no matter what imaging mode we use, and so from the user perspective, GMTSAR can handle those different imaging mode. So you could process them without worry about all these details. And so our currently we're hoping to simplify the GMTSAR processing framework, because in the past, what we do is we have those raw data, and you kind of focus the SAR image in the radar coordinates, and depending on where they are, these radar coordinates from image 1 and image 2 do not exactly align, so we have to do the correlation, so align this image still in radar coordinates, form interferogram, form terrain, and basically topography correction, and flatten the interferogram. So the data is typically designed like either as raw data or SAR image in their own coordinates. So the GMTSAR have to handle all these issues based on the user. This is part of the responsibility. We learn how to use the GMTSAR using different steps to do this step. But a very promising part is that right now there is a new algorithm that allows us to move the topography correction and also the geocoding. So instead of aligning all the SAR image to another radar coordinate, why not just align all the radar image into a long common coordinates? Then you do not need additional correlation, right? And so this is called the geocoded SLC. We hope to enable in near future in GMTSAR, and also NISAR will directly deliver the data in the geocoded SLC format, and that makes the formation of the interferogram and time series analysis much easier. So, this is gonna be a group. I'm pretty excited about this, because if you make things easier, then more people gonna use it, and then more good stuff gonna come out of that. So that's the end of this talk.
Thanks, Anne.
Yeah.
Well, there's lots of good questions coming in the Q&A, so keep those coming, but I think we can move to the Discord site. And I noticed a few people just joined in the last 5 minutes, so they probably had their time zones mixed up a little bit, but we've recorded all of this, and I think it's gonna be on the EarthScope site. Is that Moodle? Sometime this week. So maybe Melissa could remind us if she's here.
Yeah, we'll upload the recordings to Moodle first, and then after the course is over or the lectures are over, we'll upload those to the EarthScope website via YouTube.
Great. So I don't know if anybody else, any of the instructors have anything to add, or we have lots more to come tomorrow and the next day.
Yeah, we'll meet tomorrow the same time. Yeah. Today.
Hopefully it's not too much overwhelming information, but you can go back over the lectures and there will be time to sort of digest it when you do your own processing too. And yeah, so there's been great chats in the Q&A. So I think hopefully those will be posted on the Moodle also later on. But if you have any questions throughout the course while you're working on things, use the Discord to keep in touch with us. So.
Thank you. And see you guys tomorrow.
See you all tomorrow. Bye.